Hi, my name is Henry Lee, and for the week 2 video, I'm going to be talking about gradient descent. Instead of the two videos that we watched for the week, I'm just going to talk about one video made by the channel 3 Blue 1 Brown called gradient descent, but I'm going to fully explore it. To recap from what we learned last week, a neural network is a computer system in which have many artificial neurons that work together to produce a result or produce an output. In a neural network, all of the neurons from a previous layer are used to calculate a single neuron from the next. All of these to the first one, all of these to the second one, all of these to the third one, and so on until we fill out the entire second layer. And we repeat this process with the second layer to the third layer, and from the third layer to the final layer, which will be our output. And an example of neural network is a handwritten digit recognition in which we fed the computer an image of a handwritten digit, and it was split into pixels, and the same amount of neurons will store the values of those pixels, with like 0 being black and 1 being white, and all the shades of gray will be the decimal values in between. And the way they recognize the digits from the image was by like the weighted sum of their activations, or like the weighted sum of the pixels, of the values of the pixels, and rather than the actual values. What I mean by this is that they don't look at a tree and say it's a tree. They look at a tree and they look at the pixels and they add it up and that's how they would tell what values it is. But the problem with this is that the model is too simple. If you feed it a random picture, you will still get a value. If you like a random image of a zebra, they will still give you like an output, like for example 6, because they're not looking at the actual values. They're looking at the sum, at the weighted sum of the pixels, like which pixels are brighter or and in what particular location. Or like think of another way. If you fed it the image 100 images or like a half an 8 to the computer, it will equally look like a 3 or like an almost complete 8, because they're not looking at the actual values. They're only looking at the weighted sum of all the pixels. The model is too simple because it's only looking for patterns and grouping them together. Images similar to that 3 are grouped together, images similar to 2 are grouped together, but they don't know there are 2 or they don't know that 3. They're just grouping stuff that they look similar together. So how do we improve the accuracy of this model? Well, we could tell them what to look for. For example, in this example where like the result, the handwritten digit is a 3, it should have been 3 light up, so it should have been an entire 1 here. And all of the other nodes or the neurons should have a 0 because they're not 3. Only 3 is light up or should be light up. And this function is called an average cost function. We take each output and we subtract it from their actual values, like minus 0, minus 0, minus 1, minus 0, minus 0. And then like we square them together, or we square all of the differences and then we add them together. And after that, we average them. So we subtract the output from the actual values, square them, add them up, and then average. The lower this number will be, or the lower the cost, the more accurate it will be. So we want to find the minimum value of this function. In a 2D graph, we will find the minimum by looking at the slope of a point. For example, if the slope was positive, meaning it is going from left to right, we will have to move left, 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 left until we reach this valley, which will be the local minimum. But the local minimum is not guaranteed to be the lowest value in the entire function. It is only the lowest value in this local area. For example, if we started here, we'll go left, 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 left until we reach this valley, and this will be another local minimum. But this is not the lowest value in the entire function, which would be this point in this case. It is only the lowest value in this local area. But we don't really mind for neural networks because all of the local minimums are roughly equal to each other. Even if we don't get the lowest value in the entire function, a local minimum is good enough. However, a 2D graph won't be able to represent a neural network because a neural network uses more than one input, like weights, biases. So you will have to do a 3D graph. In a 3D graph, a gradient is the direction of the steepest ascent, or in other words, the direction in which it goes up the fastest. So the opposite would be a gradient descent, the direction of the uh, fastest descent, or the direction in which it goes low the fastest. And if this were a neural network graph, and or no, if this was like a cost function graph, uh, like the gradient descent would point to the minimum value of that cost function. The algorithm for this is called backpropagation to find the gradient descent, but I'm not gonna cover this. I'll cover it in this video. An easy way to show this is through a column vector that contains all of the weights of each neuron. And after finding the gradient descent, we obtain these values. And these values tell us two things. How much do we need to change the weights and in what direction, like positive, negative. What this means is that to find to find a lower cost value of the cost, to find a low cost, we have to increase this weight by 0.18, or like small increments. And the opposite is also true. For this, it would mean that we have to decrease by 0.51, decrease 0.51 on like somewhat of a bigger increment. And it is basically what we learned in the previous slides, where we had to take step until we find the local minimum. It's the same case here. We take small steps depending on the size, like small size, medium size, or high size. We take those steps until we find the lowest cost function. One thing I forgot to mention is that these values also tell us which weights matter more to the overall calculation. For example, this is 0.82. It is really big, or it is big. So it means that this weight matters more to the overall calculation of the cost function. If we're able to find the perfect weight using this, we'll basically increase accuracy by a lot. To summarize, when data are given the appropriate labels, we're able to find the minimum cost very quickly. As you can see to the right, with randomly labeled data, the graph is like almost linear. The more steps we take for the gradient descent, the lower its value for the cost function becomes. But if we compare with the data that are properly labeled, you could see like a sharp decline, or it becomes like accurate very quickly. And we take fewer steps for that too. And it's not gonna get more accurate because it started very accurate from the very beginning, because we only take a few steps because the data is labeled properly. And the reason for this is because when data are randomly labeled, the neural network doesn't know what to look for. So it just finds patterns and groups the data together based on that pattern. For example, if we find like a image that resembles a tree, but it's not exactly a tree, it's gonna group it with the other trees. A way to prevent this if I labeling the data, and we could do this by using a cost function and finding the gradient descent. So if we go back to the beginning, this is how we label the data. If the data is supposed to be a 3, you subtract it from 1. So this high value minus 1, you're going to get a low value. And if the value is low, or if the difference is low, the overall cost is going to be low. Compared to this, where like it also said the neural network is also showing that it's an 8. If it's an A here, but it's not an A in the actual value, you subtract it from 0. That doesn't change anything. So this high value remains high, and thus the cost function will remain high. By subtracting it from the actual values, you're lowering this value. But if you're subtracting it from the wrong values, you're not subtracting anything. So the value remains high and the cost becomes high. And that's why by labeling the data, we're able to increase the accuracy very fast, because the neural network knows what to look for and how to know when it is wrong. So it could not make the same mistake. And thank you.